Welcome, students. Today's lesson is going to go a little fast, but again, I am expecting that you guys can go back and look at the video if you need further clarification, and of course, we'll spend some time in class on this concept. So this is section 7.3 out of your textbook, and this is a one sample t-test for a mean mu. We're going to try to essentially accomplish the entire t-test in this lesson using skills that we already know, and we'll try a problem when we're all done with the lesson. Okay, so this is going to be very similar to last chapter. Last chapter we used a t-distribution whenever for a confidence interval for a mean whenever we did not know the standard deviation of the population. And this is going to be the same kind of criteria for a one sample t-test for mu. We use this when the standard deviation of the population sigma is not known, as is more likely going to be the case than it is known. And the idea is we're using S sub x, the standard deviation for my sample, as an estimate of the actual population standard deviation sigma. Like last chapter as well, the degrees freedom is going to equal n minus 1. And also like last time, the conditions, the conditions are going to be random, that is the sample should be random, and normal, and we'll talk about that normal condition in a few moments. The actual testing procedure is going to be the exact same as the z-test, and as you will find, the testing procedure will essentially be the same for every test that we do. That is, we need a null hypothesis, we need a significance level, we need to check our conditions to make sure we can use the techniques that we're learning. That's in this case the random and normal condition, and we also need to calculate a test statistic using the statistics from the sample, and we'll find a p-value, and from that p-value we'll make a decision whether to reject or fail to reject the null hypothesis, and then we'll wrap it up nicely with a conclusion in context of the problem, that is usually answering the question that is given. So I want to talk first about the test statistic and how to calculate the test statistic. We know how to write hypotheses, but for a t-value, the test statistic, here's what we're going to need before we actually calculate this. Now again, a statistic is simply a number that comes from a sample. So the mean of the sample, x bar, we're going to need that. That's our sample statistic mean, our sample mean. We're going to need S sub x, that's the standard deviation from the sample. Most of these can be found with one var stats on your calculator, not only most of these, all of these. We're also going to need a sample size n. So, and since this is a t-distribution like before, we're also going to need the degrees freedom, which is n minus 1. So we need all of these pretty much before we set out and calculate our actual test statistic. If you recall, our z statistic was x bar minus mu over sigma over rad n, and you'll find that our test statistic now t, and I'm going to put a little df here to remind you that the degrees freedom are important. Well, it's going to be our sample mean minus the population mean over the standard deviation of the sample divided by the square root of n. This is the test statistic. You got this? Okay, because I'm going to flip pages. Okay, I'll write them here. I'll keep going, I know. Conditions. Let's talk about the conditions. We said number one was random. That has to be given. Now, the normal condition can be satisfied in three ways. Either the population is normal, and that is given. Now, we had problems like this in the last section. What the difference is between a t-test and a z-test, many of the problems in the last section, we said, hey, the population is normal and the standard deviation, hence the standard deviation of the population is this particular value. Then we'd use a z-test, because in that case, sigma, the standard deviation, is known. But I could say that the population is normal, and but I can not give you this standard deviation, in which case you would have to compute the sample standard deviation S of x. Remember the second condition? I know you guys remember this by now. Good. Sample size is over 30. Sample size is over 30 means that the distribution of sample means is approximately normal. The last one is going to probably be more often the case, and this is the small sample size. And I say it's going to be more often the case because you already saw this on your last exam. For sample size, just like last chapter, the plot, so you should plot the data, sample data, in a histogram or box plot is nice. So the plot should show no outliers. Oh man, I'm running out of room. Or skewedness. Where should I write that? Or skewness. So we need to check those conditions. As I said, condition number 3 is probably going to be a little bit more common. I'm just going to give you a bunch of numbers, like we'll see in our example today, and you're going to have to go to your calculator and sketch a histogram and or a box plot. Can I move on? Next slide. Okay. I want to talk lastly, believe it or not, we're almost done with this lesson, about the p-value. How to calculate the p-value. Now before I switch to the last screen, what we need before we get the p-value is this test statistic, our t-score, and again we're going to need the degrees freedom. So let's talk about finding the p-value. What's your p-value? What's your p-value? So to find your p-value, you can use a table. However, I find that the tables are a little difficult to use. I will show you how to use the table in the back of your book in class. What I'm going to suggest is you use your TI calculator. And if you go to second vars, so second vars, it should above it say distribution. This is where your normal CDF is. We want the function tCDF. Now the way tCDF works is just like normal CDF. Hopefully you're comfortable with that. T distribution is centered at 0. It's bell-shaped. It's symmetric, as we've learned. And the idea is, say I have a left tail test. It's going to depend on whether it's a left or right tail test. But say I have a left tail test, and I want to find the value of, I'm going to call this T star. And let's just say it's some degrees freedom. I'm just going to call DF. Well, in this case, since it's a left tail test, it's probably going to be a negative test statistic. I'm going to put in, the general code for tCDF is upper, comma, lower, comma, degrees freedom. Just like normal CDF, except for I don't need a mean and standard deviation. In my example here, I have a left tail test, so my upper, Mr. Bessling, I'm sorry guys, I'm backwards. Why am I so backwards? Sorry for making you erase your notes. It's lower, upper, degrees freedom. If you would have had it switched around, you would have had a negative probability. Guys, don't write negative probabilities. Don't write a negative p-value. Don't write a p-value that's greater than 1. You'll lose double points for giving me a p-value that doesn't make sense. A p-value should be between 0 and 1. It should never be negative, and it should never be greater than 1. So in a right-tailed test, your lower would be, say, in a left-tailed test like this example, the lower would be negative infinity. A bunch of 9s will do it, and then whatever value your test statistic is, which would be a negative value, and then comma degrees freedom. If it's a right-tailed test, we'll call that negative t star. We'll call that positive t star. Then I'm going to do TCDF, and I'm going to put my t-score first as my lower value. Again, I'm looking essentially at the interval that I've shaded, and then 99999. Then a bunch of 9s, even 3 9s will do it. You know, that's plenty of standard deviations away from the mean. And then put in your degrees freedom. If it's a two-tailed test, I got to find the equivalent one tail, like I would just put in, the code up there, and then multiply it by 2. So let's work through an example here. Try to make it a little quick, and just to make it a little tricky, I will do a two-tailed test for the example. So we'll work through this example. And if you have your calculator out already, if you can start maybe putting those numbers into the bottom of the calculator while I read the problem. And just to let you know, we're going to kind of do the whole shebang on here. We will write the hypotheses, check the condition, calculate the test statistic, calculate the p-value. We will make a decision and make a conclusion, and maybe might just verbally want to say what a type 1 and type 2 error is. Okay, so a chain of restaurants has started a new advertising campaign. Historically, the company's stores average $3,200 of sales per day. Is there evidence at a 5% significance level to suggest that the average sales has changed? We randomly sampled 10 stores where the daily sales are listed below. So we have 3,400, 3,550, 3,100 again, 3,100 for the first time, 3,300, 3,400, 3,600, 3,250, 3,350, 3,300, and $3,450. Okay, so let's start out and write. And if you're watching this at home, you can pause it, see if you could write what the null and alternative hypotheses are. And again, look at the question that we're asking. Is there significant evidence to suggest that the average sales has changed? Has changed doesn't indicate a direction. It could be bigger, it could be lower. So should this be a one-tailed, right-tailed, left-tailed, or two-tailed test? Two-tailed. Good job. Somebody said it. Somebody in the back row said it. So the null hypothesis, again, we're still in means here. It's the average daily sales. So the average, mu is going to equal 3,200, which again was the historical average that we saw from the problem here, versus mu1 is not 32,000. Sorry, mu is not 32,000. And again, I'd like you to think about what does this value mean? Where mu, this letter mu, does it represent all daily sales? Somebody said yes. Somebody said no. Why is the answer no? The answer is no because we already knew what the historical average is. We know what the historical average is. It's 3,200. We did something new. Has it changed? So this is going to represent, the variable mu here is going to represent the mean or true average, the mean daily sales of the restaurants. I'm going to leave that part out. After the change. Again, after the new advertising campaign, I should say. So we're trying to see, did this advertising campaign have an effect? Did it seem to have an effect? It certainly kind of appeared that way. It looked like the numbers were higher. Was that just pure random chance, like the actual average didn't change? We just happened to randomly sample some stores where the average was higher? Or is there a real effect going on here? Okay, so think about a type 1 and a type 2 error in this case. I'm not going to write this down on the screen here, but think about a type 1 error would be in this case. A type 1 error would be rejecting the null hypothesis when it was true. So that would be concluding, and rejecting the null hypothesis means, we reject the null hypothesis in favor of the alternative hypothesis. So I can pretty much assume the alternative hypothesis. So I would conclude that the mean is not 3,200 when in reality it is 3,200. How could I say that in a little nicer ways? Again, what does the null hypothesis means? It pretty much means that the average has stayed the same versus the average changed on the alternative. So I could say something a little nicer, like a type 1 error would be concluding that the mean daily sales has changed when in reality it stayed the same. So I'll let you think about what a type 2 error would be in this case. Alright, we need to check the conditions. Again, this should be some kind of random sample. If it's not a random sample, I've said it 1,000 times, it's not a fair representation of the population, and there's no point in doing any of these statistical methods because they're not correct. Your sample's not random. But it did say in the problem that the stores were selected randomly. So the next one is the normal condition. And when we look at the normal condition, I usually start with, did it mention that the population was normally distributed in the problem? You don't have to look back. The answer is no, it did not. Is the sample size over 30? Nope, there were only 10 stores. Best thing we got to do now is to go, we have those numbers in our calculators in L1, and sketch a histogram. I'm going to warn you right now that I don't have my calculator with me as I'm recording this video, so the histogram I make might look slightly different than the histogram that's on your calculator. And that's just, again, how that happens is just the way they partition the classes. So this was my histogram. Again, yours might look slightly different, but hopefully it has somewhat of a mound shape somewhere near the middle, maybe around 33 or 3,400. Maybe a little bit of weird stuff on the right. But again, you know, no histogram is going to be perfect, but this is the histogram is not skewed, is not at least strongly skewed. And has no outliers. So the normal condition is met. Let's go ahead now, and has no outliers. There's my check. So let's go ahead now on the next screen here in just like 13 seconds and calculate the test statistic. In the meantime, what you're going to need to do is go on your calculator and go to 1VAR Again, I don't have 1VAR with me today, but I have R on my computer, which does the same thing. So I'm going to go to the next screen now. So the test statistics now. And I put test statistics because, again, a statistic is simply a number from my sample, and there's a few of them in this case. So I have X bar, my sample mean. Again, this should be under 1VAR 3370. Well above the claimed mean of 3,200, right? Well, could this have occurred by random chance, or was there an effect here? I have a standard deviation of 145.68. I'll round it to 2 decimal places. I have a sample size of 10, which means what should my degrees freedom be? Sample size minus 1 is 9. So I need to calculate my test statistic. That's going to be my value of t. And again, this is going to end up being with 9 degrees freedom. The degrees freedom matter. So I'm going to take my sample mean, 3370, minus the mean under the null, which was 3200, divided by the standard deviation of the sample over the square root of the sample size. And I am going to put that in my calculator. You're putting it in yours, right? So it's going to be 170 divided by I got a test statistic of 3.69. Now this works very similar to a z-score. In your experience, is this a big test statistic or a small test statistic? Yeah, this is pretty big. This is essentially over 3 standard deviations from the mean. This should give us a pretty small p-value, which should tell us that our sample was unlikely to occur by random chance if the null hypothesis is true, if the real mean is actually still 3200. So let's calculate our p-value. So I want to see sketches here. Why? Because this is going to help you that it's a two-tailed test, right? This is a two-tailed. We knew that from the beginning because the question is, has it changed? Could have gotten better? It could have gotten worse. Who knows? Maybe the advertising campaign was a joke and it actually hurt, not helped. So we were 3.69 degrees freedom. I'm sorry, standard deviations. And the degrees freedom we said was 9. Since this is a two-tailed test, we are going to have to double our p-value. But let's go ahead and just so what I would do on the calculator, since I know it's going to be a two-tailed test, but I'm going to do this part later, or well, I could do it at the same time. So I'll do 2 times TCDF, and I'm going to use this area to the right. So my lower value will be 3.69. My upper value will be infinity and beyond. My degrees freedom is also 9. I know that's a lot of 9s in a row here. And go ahead and put that in your calculator. And I have yet to multiply it by 2. I'll multiply that by 2 in just a moment. But so before I double it, let me just, the reason why I didn't, because I just wanted to illustrate that the area now in that tail is going to be just the number under TCDF. So to double it, this value over here will also be that same value. So now I need to multiply it by 2, and it's just about, with a little bit of rounding, 0.004998. So it's just about 0.005. I'm going to go ahead, no harm in rounding it at this point. We're way in the extreme values anyway. So I'll call it 0.005. Okay, so what should my conclusion be? What's up with this p-value? We're almost done. Okay, I'm going to switch sides. So my decision and my conclusion. My decision, again, is I'm either rejecting or failing to reject the null hypothesis in my decision. Which one? Reject the null or fail to reject? Okay, because my p-value, yeah, I didn't answer that, did I? I'm leaving you hanging. Because my p-value is less than my significance level alpha, we reject or fail to reject? We reject the null hypothesis. Small p-values, you get to reject the null hypothesis in favor of the alternative, which is what we were kind of trying to show here, right? Because we had a suspicion that sales would change. We weren't sure which direction, but we've essentially shown that it is extremely likely that the sales have changed. I'm not using the word prove because I didn't prove anything. There's still a small chance that I committed a type 1 error in this case. So my conclusion is I would say there is convincing evidence of the alternative hypothesis in this case. There is convincing evidence. That word is convincing. My stylus broke, so my handwriting is worse than ever. It's hard enough. There is convincing evidence that the average or mean, because this is a mean, average is a kind of ambiguous word, daily sales has changed. And again, I'm going to be specific after the new advertising campaign. Alright, as I'm just writing that, I hope this video was helpful. I'm going to end this lesson right after the new advertising. Okay, I'm going to end this lesson right about now.